Let's take a look at this example problem for projectile motion. This is a great problem to reference back to due to the fact that we have everything in terms of variables. So we can use this as kind of a general starting point for other future problems where we might know the angle, initial velocity, height, distance, all those things. This one here, we're going to solve for this in terms of the given variables. So we have here, we can see the initial starting point here, and they give us our v naught, our initial velocity, and theta, our angle here from the ground. So right here, we go from our origin here, we go up at some initial velocity, at some angle, comes up, we have some max height over here, denoted as h, and we see that it travels along the x-axis at a distance r. Now, what do they want us to find? In this problem here, they ask us to find an equation that defines y as a function of x. So we can see we have y here on our vertical axis, we have x over here on our horizontal axis here. The plan for solving this is to eliminate time from the kinematic equation. So we know we're going to need our kinematic equations. We know we're going to need to solve for time in this here. So from this information here, what we're going to do is create our setup page. So now that we've had a chance to look through the problem statement, understand what they've given us and what they're asking us to solve for, the next step is to create our setup page. And on our setup page, you want a couple different things. We want to clearly label what they've given us in the problem statement and the given diagram, what they're asking us to solve for, redraw a simplified version of the diagram or any information or charts that they give us, and clearly define a coordinate system we want to use for the solution to our problem. So we have here from our given diagram, we have clearly defined our x is positive going to the right, and our y is positive going up. We have our initial velocity here, v naught, our angle theta, our height h, and our distance r. Now they give us, even though it's in terms of variables, an initial velocity of v naught and an angle of theta. They want us to find equations that define y as a function of x. And we're going to eliminate time from these kinematic equations. So as we begin our solution, we realize that our initial velocity v naught here is in both the x and the y direction. So there's x and y components, and we want to solve for each of these separately when we're dealing with these projectile motion equations. So I'm going to break down v naught in terms of its x components and its y components here. We can do that with a little bit of trigonometry. So we come back over here and we say, okay, got this angle theta here, got my initial velocity going up in both the x and y directions. So let's look at what is the x direction, vx, and what is the y component, vy here. You can do that with a little bit of trig, and this is where, again, we can redraw out that positive y up, positive x to right, keep track of our sign convention from our chosen coordinate system. Remember, SO, CA, TOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So if we look here and we say, okay, if I need to deal with my x component here, we have my cosine. So the cosine of theta is adjacent over hypotenuse. So my adjacent over my hypotenuse involves my x component here. So cosine of theta is adjacent over hypotenuse, or vx over v naught. So I have that information there. I can rearrange and solve for that. My vx is then equal to v naught times the cosine of theta. So here's my vx component right there. Do the same thing for y. Now the sine of y, opposite over hypotenuse. The sine of theta is our opposite, or our vy over hypotenuse v naught. So opposite of hypotenuse, vy over v naught. Rearrange, solve for my vy. Move this up just a little bit for you here. So I rearrange, solve for my vy here. Vy is equal to v naught times the sine of theta. Plug that back in up here. So now what I've done is I've broken down from my initial diagram up top here, my v naught, my initial velocity, in terms of its x and its y components. So if you recall from the problem statement, what they wanted us to do in the end of this was to solve for y in terms of our variable x there. So this is why it's great to have that setup page. If we're ever going along to our solution, forget what we're actually looking to solve for in the end, we can reference back to that first setup page. So what we did in the first part was we had, in the x direction, we were able to rearrange and solve for time in terms of our x, v naught, and our cosine, where our v naught was our given value for our initial velocity and cosine was our given value for theta, even though they're in terms of variables here. Those are our two given values there. So now we have time as an expression in terms of x. So from this here, what we can do is we can plug this value for time back into our expression that we solved for in our y component direction here from our kinematic relationship there, where y is equal to v naught times the sine of theta times this time here minus 1/2 g time squared there. So we can take this expression for t, plug it in there, and this will eliminate t from this expression of y in terms of x. So we do that there, we end up with y is equal to v naught times the sine of theta times t, we plug this directly in here, x over v naught times the cosine of theta, minus 1/2 g becomes g over 2, times t squared, plug in our value for t here, x over v naught times the cosine of theta squared. Now, this is technically what they asked us to solve for, but let's go ahead and break this down, simplify and reduce it to get an easier expression. Now, if they've given us values for theta and x and everything else, we just plug this into a numeric solver or calculator and be done with it. But in this case here, they want us to solve for a nice simplified expression of y in terms of x. So we're going to use some trig identities, simplify things down. And what we're hoping to find, our goal, is to get it into this form here. So many times in this text and other texts, you'll have selected answers in the back where you may only have your answer here. You need to know you need to get from this point to this point. So this will be a good practice here. What are the trig identities? How do we simplify and reduce to get from this expression down to this expression here? So what we can do is we're going to use our trig identities here, our reciprocal identity, which we recall is the secant of x is equal to 1 over the cosine of x, and our Pythagorean identity, which says that our tangent squared of x is plus 1 is equal to our secant squared of x. So we need to get from this expression to this expression here. First thing I want to do is just combine a couple things together to simplify this down. So the first thing that I notice is this is a sine over a cosine. That's going to be a tangent there. So that'll be the first thing I want to do is combine these two together, put the x on the top, or a sine over our cosine there, and reduce this down to a tangent of theta there. Then from there, we can take a look, see what everything else form has taken, and then decide where we can plug in these identities. So I'm going to leave my previous page up here so I can just see where I've gotten as far as my expression for y in terms of x. Again, what it says, I'm going to combine these two together here, and when I do that, I see there's a v naught and a v naught that can cancel. We have a sine of theta over a cosine of theta, which can reduce down to a tangent of theta. I have my negative g over 2, and then I'm going to distribute this through here, so this ends up, when I do this out, of x squared over v naught x squared times the cosine of theta. So I can pull these two guys out here with my g over 2, which leaves me with this 1 over the cosine squared of theta here. So if I scroll up a little bit now, go back to my trig identities here, I can look at both of these in line with us here. Can look at this here. So if 1 over the cosine of x is the secant of x here, I can say that this right here, 1 over the cosine squared of x is my secant squared, or so of theta is my secant squared of theta here. When I sub in, it's generals in terms of x, ours is in terms of theta here. Plug that in, so now I've used my trig identity, the reciprocal identity, to get from 1 over the cosine squared of theta to the secant squared of theta here. Then I've eliminated that. This simply is the tangent of theta times x minus g x squared all over 2 v naught squared, now times this from our reciprocal identity here. So now the next thing we can do is we can use our Pythagorean identity at this point here to reduce it down a little bit more. And what we see here is tangent squared, in our case of theta, plus 1 is equal to the secant squared of, in our case, theta here. So we can reduce this down. So secant squared of theta, going backwards on this, is equal to 1 plus the tangent squared of theta here. So now I have everything just in terms of tangent and tangent, and got rid of that secant there. So this is my answer here of x times the tangent of theta minus gx squared over 2v naught squared times 1 plus the tangent squared of theta. And if we go back up to what our goal was for the form for a general expression of y in terms of x, now we can see that we have achieved that here. This was what we wanted to get to using a couple trig identities. We're able to get down and get that expression in the right form.